We're just waiting for the... Okay, so we're recording. So this is the third lecture, and the point of this lecture is to look at the first term in the Bloch equation. There's just four parts of it, and then but that will immediately make us have to deal with the cross product. And so then I'll talk about dot product, cross product, and complex multiplication, which are three distinct kinds of multiplication with vectors. And then and that will take up the whole time. And then hopefully at the end there should be about 10-15 minutes for questions. But you can also stop me. I should be able to hear you. So if you ask a question, I should be able to hear you, and you should, of course, be able to hear me. And then, of course, it will still all be recorded, and so you can always go back to the recording. So let's get started, unless there are any other questions. Looking over there, give you a minute to unmute if anybody has a question. Okay, so let's. This will be smoother next time. All the rat's nest of wires are all correct now. Okay, so what we want to do is try to explain how the precession works. So what are the equations for the precession? And so that's what we're going to be talking about. And so what does the first term of the Bloch equation look like? So the first term of the Bloch equation looks like this. It says, for a small amount of time, if we look at the current state of the magnetization vector for a small amount of time, how does it change? So that's what the meaning of that vector derivative is. It says, what is the change in the current magnetization vector, which itself is a vector. So the current magnetization vector is a vector pointing in some direction. And what we want to know is, like, what's it going to do next? And that is a vector of its own that says, how is that going to change? So that's that first. That's the left-hand side of the Bloch equation. This is the Bloch equation, term 1. And then what that says is that's equal to the current state of the magnetization vector cross-producted with this thing. So what is that thing? That's the B vector multiplied by that gyromagnetic ratio. So that so this guy is a constant, and this is just the main field. So we're not going to have any gradients on. This equation can deal with gradients, and it can deal with the RF, but we're not going to have any gradients on and no RF. So we're just trying to understand the precession. And then this thing is just the current state of the local magnetization. Loc mag. So what that means is that's just whatever the bulk magnetization, so this is like magnetization within a voxel. So if you added up all those spins that were either sort of on the cone that's lined up with the magnetic field or the cone that's opposite to the magnetic field, added up all those vectors, tip to tail, and we ended up with the bulk magnetization of that voxel. So what direction is the magnetization of that voxel at an instant in time? So that's what this is. So this is the current state of the local voxel magnetization. Okay, so and then that's just the first part of the Bloch equation. Then there's other terms which we'll talk about on Monday. So that's just the first part. But it immediately brings up the problem of the cross product. And so if you're like me, you haven't done the cross product in a while, and so what we want to do, so the way math works, so how does math work? Math works by compressing a whole lot of stuff into one thing. So like there's just m. A lot of times it might not even be written with the vector sign over it. And what does that mean? Well, that stands for a three-dimensional vector pointing in some direction with some length. So the problem with math is everything is written in this very compact form. And there's a reason for that. It's a good reason for that, because that's actually that's the way you eventually learn how to think. You just think with these compact, dense units that have all these implications, but they're just a single letter, typically, just one letter. And so what we want to do, if you're like me and you haven't done any math, we have to unpack those things into what the meaning is. So this thing, like that cross product symbol there, will stand for a whole set of multiplications. So it's on the positive side, it's just multiplication and addition. It's just like different patterns of multiplication and addition. But there's a whole bunch of stuff embedded in that. And so that's what we want to do today, is just sort of systematize the thing and write it out. So if we start off with adding vectors, so because this is all about multiplying vectors. So if we add vectors, that's easy, actually. And in the case of, the dot product, cross product, and complex multiplication, those are all different. But the adding case is all the same, including for adding for complex numbers, which you can think of as vectors. And so basically, if we add a two-dimensional vector, so here's a two-dimensional vector, C equals a two-dimensional vector A plus B. How do we do that? Well, there's two different ways of doing it. So one way of doing it is we take one vector, so that's vector A, and then we take another vector and we just do it tip to tail, and then that gives us our answer vector. So here's the B vector, and there's the C vector. So that doesn't really require any coordinates. That just says, just tip to tail. But you can also do it by putting on a coordinate system. So if you put on a coordinate system like this, then what we can do is an alternate way of writing it out is as a little matrix, a little one-row matrix, and that would just be the x-coordinate of A plus the x-coordinate of B. That's how you get the x-coordinate of C, and then the y-coordinate of A and B add together. And so what does that look like in the graph? Well, here's the x-coordinate of here's a x, and here's a y, and then now we have to draw the vector over here to get its coordinates. So let's put that B vector over here, and now we can get its bx and by. So if we just add ax and bx, so bx is negative, so it subtracts off, and that will give us this x-coordinate of C. And then if we add the ay to by, we get this y-coordinate of C. So that part's easy. So adding vectors is easy. There's only one way to add vectors, basically. We just do tip to tail, or equivalently, we stick some coordinates onto the whole thing, and then just add the x's and add the y's. So, and this generalizes to every dimension. So this works in 10 dimensions or 30 dimensions. We'll see that the cross product doesn't generalize. Okay, so now let's start with sort of writing out the cross product. But before we do that, let's let's just write out the dot product, because the dot product and the cross product are kind of related to each other. And we're going to write it out in like 1, 2, 3, 4 different ways. So you can sort of see, just drill down to the absolute bottom and just see what the relationship between all these things are. So if we start off, with the dot product. So dot product it's written like a dot because you use a dot when you're trying to indicate multiplication. And the dot product is a weird kind of thing. It actually turns the two vectors into a number. So the dot product takes the two vectors A and we dot them with B. And the result we get is just a number. So this guy is just a scalar, a number. And that it will always be a scalar no matter how many dimensions the vectors have. So these could be 3-dimensional vectors, then you still get a number. 10-dimensional vectors, still get a number. And that number, this particular number, is an interesting number. It basically tells you how similar the vectors are to each other. And it's essentially the correlation of the vectors. This is really how you define the correlation between two things. And so how does it, when you peel it out, how does it, just into numbers, what does it look like? Well, we can write it out as a matrix multiplication. So we'll say what that means. So here we have bx, by, so we'll do it for 3-dimensional vectors, bz. Okay, so that's a matrix, a one-row matrix, and we're multiplying it by ax, ay, az. So when you see that, what does that mean? Well, that means when you multiply matrices, the rules are, it means you multiply b times a, you multiply bx times ax, and then by times ay, and then bz times az. And you can do this for vectors. You can do this for a vector and a matrix and a vector. You can do it for two matrices. So those are the rules. And so let's just write out those rules, the result of those rules. And so the rules are we multiply the x components, and then we add them to the y components multiplied by each other. Sorry. A, y, b, y. And then we add them to the z components multiplied times each other. And so then we end up getting a number out of this. So this is just a number. So we turn these 3-dimensional vectors into a number. And what does that number say? It basically says how similar the two vectors are to each other. But it turns out it also has an interesting property that it equals this other thing. So it equals the length of the vector, of the first vector, I'll say how you calculate that, times the length of the second vector times the cosine of the angle. So what does the cosine look like? So let's draw out our cosine. So here's a cosine like 0, 360. Goes from 1 to -1. So the cosine sort of starts up at 1, it goes down, and then it goes back up again like that. That's the cosine. So you can see when you're at 0 degrees, the cosine is the biggest, it's 1. And this is, what is that cosine, relative to? That's the cosine between the two vectors. So I'm going to erase the simple adding of vectors here. So it's the cosine between, let's draw the picture here. So here's, let's say that's the A vector, that's the B vector. So it's the angle between those. That's that angle between those. And so if the angle is 0, so they're lined up with each other, then you get the biggest number. You notice if the angle is 90 degrees or 270 degrees, so if it's this way or that way, if they're perpendicular to each other, then the answer is going to be 0. So the dot product is 0 when they're perpendicular, and then it's greatest when they're parallel. So that's, you can sort of, it's related to the idea of correlation. So if they're, it kind of measures how similar two vectors are to each other. Okay, so, but we didn't explain this. So how does this equation actually work? So this equation actually works if you look at, so what does this mean? What does that mean right there? So if we do it for three dimensions, so what's the equation for calculating the length of a vector? So if we do it for 3 dimensions, basically it's the square root of the ax plus bx squared plus ay plus by squared plus az plus bz squared. So that's just the Euclidean distance. So since those are just the coordinates of the c vector, that would be the same as cx squared plus cy squared plus cz squared. So if you look at that, that's kind of if you look at the, sorry, that was the length of c. That was the length of c, not the length of a. So if you do the length of a, it's just going to be, let's just do the length of a there also. So what is the length of a? The length of a is just going to be, ax squared plus ay squared plus az squared. That's the length of a. So when we boil this down, we have this interesting thing here where you basically have a relationship just between sort of multiplying pairs of numbers, and then suddenly magically you get a cosine out of it that is related to sort of the angle between the numbers. It's kind of magical. That's kind of the fun part of math. There's one thing you notice about this is this equals is one last bizarre thing. So this pretty much equals the square root of the dot product of A with itself. So if you take A and then dot product into itself, that's A times AX, B, AY times BY, AZ times B, AZ times A, AZ, just square each of them. You get this. That's what this is. Take the square root of it. So that's all of basic linear algebra, sort of trigonometry for the dot product. So the dot product generalizes to any d, any dimension. So you can do that for, if you have like two 20-dimensional vectors, you want to measure how similar they are. And we need the dot product when we start talking about how does a head coil pick up an actual signal. So it's a generally useful thing to have. And like I said, it's just related to correlation. Okay, so now let's get to the cross product. So the cross product is kind of a bastard multiplication. It only works in 3D, the particular cross product. So let's draw out the vectors for the cross product. So here's a b vector, and let's put a b vector there and a vector there. There's the angle between them. So the cross product gives you a vector that is coming out like that. And that vector coming out is perpendicular. So this guy it's perpendicular to this guy and perpendicular to this guy. So it's perpendicular to the plane defined by those two vectors. So any two vectors, no matter what direction they're pointing, just think about it, they could be pointing in any old direction, will define a plane. And then the cross product is going to be perpendicular to that plane. So there's the C cross product. Now the problem, you might notice, it could be perpendicular the other way. So how do you figure that out? And so you figure that out with the right hand. There's another right hand rule. And so this right hand rule, it's a useful one for trying to figure out what direction the cross product points in. And the way this right hand rule works is it works like this. Your fingers go from A to B. Make sure I'm doing that right with the learning glass. Yes, looks good. So the fingers of your right hand start at A and they curl toward B. And then your thumb basically points, it gives you the direction of the cross product. So one thing you know about the cross product is that if you reverse the order of it, you get the negative. So if I do A cross B, it will stick out. Sorry, I was pointing the wrong way. It will stick out. If you do B cross A, it's going to stick in. So it doesn't commute. So if you look at A and B in the dot product, it doesn't matter what order you do them in. You could just look at the equation for it. You can flip these, doesn't matter. AX times BX is the same as BX times AX. So the order of the dot product doesn't matter. The order of the cross product does. So let's write that out. So now we're going to get a vector. So the cross product gives us a vector instead of just a number. And so here's our so A cross B. You remember that it would be a different answer if it was B cross A. Doesn't commute. And we can write this out as a bizarre, but somewhat bizarre-looking matrix now. And I've done the cross product many times because I need to calculate. One of the things you use the cross product for is in computer graphics to calculate lighting. So if you've got a little polygon, you want to figure out how bright it should be. Well, it depends on what the angle of the light hitting it is. In order to figure out that, you need to figure out what's the perpendicular to the polygon. So you have to do this kind of calculation all the time. I can never remember it, so I still have to look at my notes to minus by bx minus bx. There's a pattern to it. By and then another minus bz. I got a mistake. Okay. So there's bz there and bx minus bx and by minus by. Okay, so that's this weird matrix, and then this guy is multiplied by our vector. Ax, ay, az. Okay, so now we've got more things to multiply out. So if we write them with the a's first, we'll end up with the following thing. So so how does this work? This means like 0 times ax, bz times ay, plus minus by times az. So let's write that out. So, and we're going to get a vector out of this. So this is a matrix multiplying a vector. That gives us another vector. So here's the vector. So it's got ay, bz minus az, by. So now we're mixing coordinates. Here we were using the same coordinates, but now we're systematically mixing them. That's the x component of the vector. And now we got az, bx minus ax, bz. So that would use the y's and the z. This is use the x's and the z's. That's the second, that's the y component of the vector, and then here's ax, by minus ay bx. That's the third component. Okay, so what does this one equal? So equal, this is only the length, because remember, this guy's a vector, so it's a three-dimensional vector, so you need three numbers to tell which direction it's. But if we do this operation on it, this operation, figure out the length. So if we figure out the length, what do we get? We get, so another way to write it is, here's the output vector, and we take the length of it, and that equals the length of the A vector, just like we did up here, times the length of the B vector, times the sign. So you can see these things are very intimate. The cross product and dot product are very intimately related to each other. So what's the sign? Well, the sign would be, something that would look like this. It would sort of go up there, and then it would go to 0 here, and then up here, and then over here, like that. So in this case, when you're at 90 degrees, the sign is the biggest. So the cross product is kind of the opposite of the dot product. When you get out to 90 degrees, it's largest. When you get it to be parallel, then the sign will be 0. So that's the cross product. And so there's a very cool, if you want to read any sort of math, there's a very cool branch of math called geometric algebra, where they kind of combine dot products and cross products. They're clearly related to each other, because you got the sine and cosine, you got all this length stuff going on. So you can sort of bundle them all into a single thing. But most physicists use cross products. And so why do they use cross products? Because they're really handy. It's kind of a really handy hack. So one thing about it is, however, only 3D. This only works in 3D, the basic cross product. Now if you do geometric algebra, then we can generalize something that's kind of like a cross product into more dimensions. But this one only works in 3D. Okay, so that's dot product and cross product, and it's used all over for all different kinds of things in physics, like tops and protons. And so now we want to, last but not least, so let's just say one more thing about the cross product. The cross product is kind of weirdly different than the dot product. Like you get a vector instead of the first sign is you get a vector instead of just a number. But what is the cross product really, what is it really like? Well, what it really represents, you could sort of think of it more as an area. Because if this is the A vector and the B vector, if we take the cross product of them and then find the length of the resulting vector, so the length of this guy, like this guy over here, so this is, length of result. What do we get? We get the area. We get the area. So we get the area, if you take the B vector and sweep it along the A vector and fill in that whole area, that parallelogram. So that's what the cross product is. So this guy actually equals the area. So the cross product is it's different than the dot product. The dot product is like, how similar two vectors are to each other. The cross product, when you do it, it gives you the area. So it gives you something having to do with kind of like a plane. That's really kind of the feeling of it. But when you do the cross product in this special 3D hack version of the cross product, of the outer product, you end up with the perpendicular vector, which is how we're going to use it. Okay, so that was the cross product. And now, last but not least, there's complex multiply. And unfortunately, that's even yet different. And so what is complex multiply? Well, complex multiply is multiplying complex numbers, and you can think of a complex number just as a two-dimensional vector. That's one easy way to think about a complex number. And so a complex number, let's draw out some complex numbers. So if we put the, the real axis this direction and the imaginary axis this direction, you can just think of a complex number as just like a vector. So here's the real part of it, over here, and here's the imaginary part of it. And you can see immediately it's going to be related to cosines and sines. So if that's the complex vector A, so now the question is, if we've got complex vector B, say B over here, how do we multiply those? So going back to how do we add them? Well, adding is easy. Just add the real parts and add the imaginary parts. That's just like, so this guy has a real part here and an imaginary part here. So that's not a problem. We can add them. But the multiplication of complex numbers is different than the multiplication of a cross product, different than a dot product. And so how does that work? So in this case, we've got a complex number. We'll just draw it out as a vector. And we're doing this complex multiply operation. A lot of times you don't even put when you're multiplying complex numbers, they may or may not put a dot. Usually they don't. So they wouldn't even put this guy in parentheses. You might just put two complex numbers next to each other indicating you're supposed to multiply them. So how do you do that? We have to do this to understand the Fourier transform. So it's the Fourier transform is adding and multiplying complex numbers. So we must understand how to multiply complex numbers. And so that gives us yet another strange matrix. So one way to write out a complex number is you can write it out as a matrix. And so here's example of writing out that complex number as a matrix. So it's bx minus by, not minus by, not minus bx again. And so if we multiply that times this two-component complex number, then we get something sort of like the cross product, but not quite. So it's going to have a two-component number, so it will be ax times bx. So here we're multiplying something that's sort of like the dot product, minus ay times by. So here we multiplied the same components. That's the x component, the real component of the product. And then now we're doing something that's like the cross product. So ax times by. But unlike the cross product, we've got a plus in here. Ay bx. So that one's mixing the two coordinates. Now, in contrast to the dot product and the cross product, when you do the complex multiply, if you take the resulting length of the resultant, which I'll draw out in a second. So that's the result here. What does that equal to? Well, it turns out that's just equal to the length of the two vectors multiplied by each other. No sine or cosine. So that's kind of convenient, because what that says is that it doesn't matter what the angle between them is. When you multiply them, all you do is you just take their lengths and multiply their lengths. So they kind of act like regular numbers. Complex numbers sort of act like regular numbers when you consider the length of them. That you just multiply them just like you would multiply two regular numbers that are not vectors. But then, what about the angle that results? So it turns out the way complex multiplication works is you just add their angles. So here's the angle of the first vector, and here's the angle of the second vector. So what's the angle of the result? Just add them. So basically the angle of the result will be out here like this. So that's the C. So the length of that thing will just be the length of A times the length of B. That gives you the length of C. the edge here. I'll put it there. It's still not on the edge. Okay, one more time. Okay, finally got it. And then the angle of C is just going to be the addition. And so complex numbers, so you can sort of think of complex numbers as, so we thought of the cross product as kind of an area or something having to do with a plane. Complex numbers you can think of them as a rotation. There's a rotation and a scaling, because potentially it could be a scaling. If you multiply by a complex number that happens to have a length of 1, say you multiply by b and b has a length of 1, then it won't scale it. It will just rotate it. And that's often, you'll often see that. We'll see that in the Fourier transform a lot, where you end up with a, with a complex number that has a length of 1. And so when you multiply that, that's just a pure rotation. So complex numbers give you a 2D rotation. Now, this is only 2D. So everything's just so asymmetrical, isn't it? So this is only 2D. But it turns out there's a 3D version of it called quaternions. Oh, it's okay. So there's a 3D version called quaternions that's very handy for, they use this in any kind of sort of, they heavily used it in the space program to sort of like stabilize aircraft and efficiently calculate rotations. And if you look at geometric algebra, you have like an NED version of complex numbers. So that's the, so that's this strange sort of just all lined up so you can sort of drill down. So this is, all we're trying to do is just figure out what goes on here. So now let's just take 2 minutes just to sort of, maybe what I'll do is I'll stop here and then we'll apply this to the actual precession, and we'll just sort of take 1 more minute to just review what we went over. So what we went over is first, adding vectors is easy, just tip to tail, or add up their components, add up the x components, add up the y components, add up the z components, or however many dimension components. So that's the same way that you do complex addition or vector addition. They're all the same. But then we have 3 different ways of multiplying them. So the dot product, we have something that's kind of measures it's just a single number. It turns vectors into a number that measures how close they are to each other, basically. And then we have this cross product, which is a weird thing, which somehow sort of says something about area and gives you a vector that's perpendicular to these 2 vectors. And then you have to use the right-hand rule, which is move your fingers from A to B, and then that tells you that C is coming out at you. And then we have complex multiply, which is yet different, which is kind of like a rotation, really, or a rotation and a scaling. So it says that the complex multiply says, take the lengths of the vectors and multiply them, and that's the length of the result. Take the angles of the vectors and add them, and that's the result. So it has to do, and if you have a vector, if you're multiplying by a complex number that has a length of 1, then it will just give you a pure rotation. And we need that, like I said, we need that to understand what the MRI signal is. This is what the MRI signal is, a complex number. And we need it we definitely need it for the Fourier transform. Okay, so any desperate question here at the last minute before I stop the recording? So I'm going to stop the recording, and then we'll start up the next recording at 9 o'clock. But we can leave the Zoom session up. Don't mess with the Zoom session. Just leave it up. But we'll just stop the recording. You should still see the feed, but the recording will be stopped. Okay, David, you can stop.